Yummy.
Oh, yeah. Mwah. Mwah, mwah. Oh, yeah. Mwah. Mwah, mwah, mwah. Oh, yeah. Mwah, 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 mwah.
Wake up! Wake up! You have to get up! It's time to go teach math class. Come on! Get up now! Let's go!
No!
Is it time for math class already?
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes Hopital. Calculus, early transcendentals, hyperbolic catenary. Calculus, learn real world models when you make it to Calculus 3.
Welcome back once again, calculus students. Today's a little bit of a sad day because this may be the last video in our series. Today's topic is L'Hopital's rule. L'Hopital's rule is a rule or a formula that helps us evaluate limits. You may remember some of these examples from way back. For example, the limit as x approaches 1 of x squared minus 1 over x minus 1. Now this limit wasn't terribly difficult to evaluate, but you do recognize that we had to do some algebraic simplification so that we could evaluate the limit of the simplified version by direct substitution. And you may remember this one, the limit as x approaches 0 of sine of x over x. This example required some very subtle reasoning to resolve. It turns out that L'Hopital's rule makes both of these examples very easy because it takes advantage of properties of derivatives and how they connect to the limits. The namesake for this theorem is not actually the person who discovered it. The actual discoverer of this rule was one of the Bernoullis. Today we'll learn how this limit rule works, and we'll practice plenty of examples.
Welcome back, calculus students, to this final installment of videos for this quarter. The topic for today is L'Hopital's rule. This is a rule for computing limits, and it works on the kind of limits that used to give us more trouble in the past. Let me give you a few examples of the types of limits that this rule would apply to. So this first example that I have here, the limit as x approaches 0 of sine of x over x. When you try to substitute x equals 0 into that thing, then direct substitution yields sine of 0 over 0, which is just 0 over 0. And of course, 0 over 0 is an undefined term. And so direct substitution doesn't work on this. But you may remember in the past that I told you, hey, when we see 0 over 0, maybe we can do some algebraic manipulation or something to simplify this thing and be able to solve it. On this one, though, you can't really do any algebraic simplification. And you may recall that I spent a good deal of effort in one lecture arguing that this limit actually comes out to 1. It's called the fundamental trigonometric limit. The second example here is similar in that when you do direct substitution of x equals 1 in this second limit, you would get natural log of 1 over 1 squared minus 1, which is 0 divided by 0. So it's another example where when you do direct substitution, you get 0 over 0. And it's another example where you're not really going to be able to do any algebraic manipulations to simplify that expression so that maybe you can evaluate the limit. So both of these are examples of what are called indeterminate forms of type 0 divided by 0. And they're called that because when we try to do direct substitution, that's what you get, 0 divided by 0. Now we did see in the past that there are times when you have a 0 over 0 form that you can do some algebraic manipulation and actually end up being able to evaluate the limit. This example here where we do the limit as x approaches 1 of x squared minus 1 over x minus 1. Now you can see plainly that direct substitution yields 0 over 0, so this is a 0 over 0 indeterminate form. But on this one, you can see a way to do an algebraic manipulation so that you can cancel off the term in the denominator that's causing the 0 in the denominator when you do direct substitution. So on this example, we could do something like, well, factor the numerator there, and it factors into x minus 1 times x plus 1, all divided by x minus 1. And then you go, aha, I see something that cancels. So you get your canceling stick out and you cancel off those x minus 1 factors. And then the limit that you're left with is just the limit as x approaches 1 of x plus 1, which we can do direct substitution into, and we get 2. And of course, other times, as we pointed out previously, there are examples where you're just not going to be able to do any algebraic maneuvers like we just did in the previous example, like this one that we mentioned at the top a minute ago. You know, with that natural log of x in the numerator, I just don't know of any algebraically equivalent way to express natural log of x that will cancel off the factor of x minus 1 in the denominator that's causing a problem. So this is where Hopital's rule is going to be really helpful in solving limits like this one in blue here. So let's see the rule and do a few examples of how to apply it. So here is Hopital's rule. Hopital is just hospital in French, but the rule is named after a person who wrote a calculus textbook back in the old days, like maybe it was the 1700s. But the person by the name Hopital wasn't actually the person who invented the rule. This was actually one of the Bernoullis who invented this rule. I think Bernoulli was this person's tutor and anyway gave the rule to the guy. But anyway, it's now known as Hopital's rule. And this one applies to these 0 over 0 indeterminate forms. So it's important that you understand that the rule that we're going to be talking about only applies to these indeterminate forms where when you do direct substitution, you get 0 over 0. Actually, it'll apply to other things, but we'll talk about that soon enough. So the setup is, suppose that you have two functions, f and g, and they're both differentiable on some interval that contains the point a that you're taking the limit toward. And we need to assume that the derivative of g is not equal to 0 on that interval, except for possibly at x equals a. And so if it's the case that the limit of f and the limit of g are both equal to 0 as x approaches a, then if you want to take the limit as x approaches a of f of x over g of x, so since limit of f and limit of g are both 0, this is 0 over 0 form, it turns out that this will be equal to the limit as x approaches a of f prime of x over g prime of x. So this is a pretty nifty rule. To take the limit of the original fraction, it's equivalent to take the limit of the ratio of the derivatives. So basically you just differentiate the numerator and the denominator separately in that fraction, and then take the limit of the new fraction that you get, and you'll get the same answer. So that's the Hopital's rule. And then this rule also works if you replace x is going to a with either right or left-hand limits as x approaches a, or you can allow x to go to infinity or negative infinity on this limit too. And one other thing that's important is that these two limits are equal, but it only makes sense if the limit on the right exists or it evaluates out to plus or minus infinity. So if you try to do Hopital's rule here and the limit that you get, it just turns up does not exist, then it doesn't mean that the original limit does not exist. It just means that Hopital's rule doesn't work in that case. So anyway, let's see a few examples of how you'd apply it. Okay, in this first example here, we want to take the limit as x approaches 1 of natural log of x over x squared minus 1. Now, those functions are differentiable, and when I do direct substitution in the numerator and denominator, I see that this really is 0 over 0, because if you take natural log of 1, that's 0, and then 1 squared minus 1 is also 0, so you get 0 over 0 upon direct substitution. So this is the kind of limit for which the Hopital's rule applies. So if we apply the Hopital's rule, then this would be the limit as x goes to 1, and then the derivative in the numerator is 1 over x, and the derivative in the denominator is 2x minus 1. And now I have to see, does that limit exist? So let's think about what we've got now. So after you apply L'Hopital's rule, one quick thing you can do is just try to do direct substitution and see if you still have a problem with getting 0 in the denominator. So if I plug 1 into this ratio that I have here, I see that I get 1 in the numerator, and then I get 2 minus 1 in the denominator. Well, that's not 0 in the denominator. So I can just evaluate this one by direct substitution, and I get 1 over 2 minus 1, so that's just 1. So this limit comes out to 1. Pretty nice, huh? Sometimes you need to apply L'Hopital's rule multiple times, as in this next example. So first of all, let's check that this is the kind of limit to which L'Hopital's rule applies. In other words, let's see if it's a 0 over 0 indeterminate form. So if I substitute x equals 0 in here, I know that that cosine of 3x term, if I plug in x equals 0, I get cosine of 0, which is equal to 1. So in the numerator there, I'm getting 1 minus 1, which is 0. And then down in the denominator, I'm getting 0 squared, which is 0. So this is a 0 over 0 indeterminate form. Very important that you check that it's a 0 over 0 form before you apply L'Hopital's rule, because if you apply it to something that's not a 0 over 0 form, you may get the wrong answer. So now applying L'Hopital's rule, which I'm indicating with the little L apostrophe H there above my equal sign, this would be the limit as x goes to 0. Our derivative in the numerator, well, the derivative of 1 is 0, and then the derivative of negative cosine of 3x is going to end up being positive 3 sine of 3x, using the chain rule there. And then the derivative in the denominator is 2x. And so now we need to think about what happens if we try to do direct substitution here. Well, if I plug x equals 0 into the numerator, I would get 3 times sine of 0, which actually equals 0. So, and then 0 in the denominator too. So this is another 0 over 0 form. So we can apply L'Hopital's rule again, since it's still of the form to which L'Hopital's rule applies. So use L'Hopital's rule one more time by taking a derivative of the numerator and the denominator separately. Okay, now the derivative in the numerator is going to be 9 times cosine of 3x, using the chain rule again. And the derivative in the denominator is 2. And now I clearly see that I'm not going to get a 0 in the denominator. That's good. So now I can just directly substitute into this, and the limit will come out to 9 times cosine of 0. Cosine of 0 is equal to 1, so it just comes out to 9 in the numerator. And then you get 2 in the denominator, so 9/2 is the answer. You wouldn't have guessed by looking at that fraction at the beginning that the limit would come out to 9/2. I suppose you could look at a graph of that function and see, and then zoom in around x equals 0 and see that 9/2 is actually the correct answer. Looking at it from or verify it graphically. But there's no need. The algebra is simple here, and it works out nicely. I would like to give you a quick rundown of why this L'Hopital's rule is true. If you're not one who cares too much about why these rules are true, then you can feel free to skip to where I start the next example. When I was a student, I never really liked rules that came from on high or out of the sky, like passed down on some tablet from the ancients or something. I like to understand why things work. Maybe that's why I became a mathematician. But I always felt like it just made me feel assured that what I'm doing makes some sort of sense. I'm not going to give you the full proof of L'Hopital's rule because it's kind of hard and it involves some stuff that we haven't really talked about in this class. But if you just look at the case where when you do direct substitution into the numerator and the denominator, you get 0. So f of a and g of a are equal to 0 in this limit that we're looking at here. So suppose that you're getting 0 over 0 upon direct substitution. And suppose that those functions f prime and g prime are continuous, and that g prime of a is not equal to 0. So these simplifying hypotheses here will allow us to do something kind of cool. Under these simpler hypotheses, I could take this limit of f over g like we have here and write it as limit as x goes to a of f of x over g of x. But then I'm going to add 0. So I'm going to do minus f of a in the numerator, and I'm going to do minus g of a in the denominator. All because we're supposing here that f of a and g of a are equal to 0. I'm not really doing anything, right? I'm subtracting 0 in the numerator and the denominator, which doesn't amount to anything. But it's kind of nice. And then what I can do from here is multiply by 1 in a smart way. So what I'm going to do is I'm going to divide the numerator and the denominator by x minus a. So I can write this as f of x minus f of a over x minus a divided by g of x minus g of a over x minus a. So what I really did here was just divide numerator and denominator by x minus a. And then if you look at those fractions, you notice that those are the fractions you take the limit of to get the derivative. So I can write this as the limit as x goes to a of f of x minus f of a over x minus a all over the limit g of x minus g of a over x minus a. So this is the quotient rule, or the quotient law for limits. And then that limit that's in the numerator is f prime of a by definition of derivative. And the one in the bottom is g prime of a by definition of derivative. And so this is just definition of derivative here. And I can do this because those limits exist and the one in the denominator is not equal to 0 by our hypotheses. So that's it, right? Since we're saying that the derivative is continuous, I can express the derivative in the numerator as the limit as x approaches a of f prime of x. And also we assume that g prime was continuous at a, so this is the limit as x goes to a of g prime of x in the denominator. And so this was because f prime and g prime are continuous at x equals a. You may remember that continuous just means that the limit that you get is the same thing you get when you do direct substitution. So if you compare the previous step to those limits, you're just doing direct substitution. So anyway, that's it. That's the ball game, because we just showed that the limit that you started with at the beginning, the limit of f over g, ends up being exactly equal to the limit of well, maybe I could do one more step and write this as just one limit as x goes to a of f prime of x over g prime of x like this. This would just be using the quotient rule again, quotient law. But yeah, I mean, that's the Hopital's rule. So there you go. That's why it's true. It gets a little harder if you don't have some of these hypotheses about things being equal to 0 in the denominator and whatnot, but that's basically the gist of it. And that proof basically works for almost anything that you ever do anyway. All right, so now let's look at another version of Hopital's rule. So this is the version of the rule that applies to what we call infinity over infinity indeterminate forms. So just like with 0 over 0 indeterminate forms, an infinity over infinity indeterminate form is basically whenever you evaluate the limit in the numerator and denominator separately, you're getting either plus or minus infinity in the numerator and in the denominator. For this rule to work, we have to have that both f and g are differentiable on an interval that contains a, that's the value that x is approaching, and we have to assume that g prime of x is not equal to 0 on that interval except for possibly at x equals a. And then we assume that the limit of the numerator is going to plus or minus infinity, and the limit of the denominator is also going to plus or minus infinity. So if all that's true, then Hopital's rule says that the limit of f over g as x approaches a will just end up being the limit as x goes to a of f prime of x over g prime of x. So good news, it's the same rule. It works exactly the same way as when you have 0 over 0 indeterminate forms. So infinity over infinity and 0 over 0, you do them the same way using Hopital's rule. And this rule also applies whenever x is going, you're doing right or left-hand limits, like one-sided limits, or if x is going to plus or minus infinity, it also works. And again, it needs to be said that this rule only gives you the right answer if the limit that you get from Hopital's rule exists. So if you do the limit of the derivative over the derivative, and you get something that does not exist, you can't say the original limit doesn't exist. You just have to try something else. Okay, so let's look at this example here. The limit as x goes to infinity of x squared plus 5x over each of the 2x. You can see that as x gets large, the numerator is certainly going to infinity. And also we know from properties of exponential functions that if you take e and you raise it to a giant power, you get a giant number. So the denominator is going to infinity here. So this is an infinity over infinity indeterminate form. So we can use L'Hopital's rule to try to solve it. So by L'Hopital's rule, this would be the limit as x goes to infinity. The derivative in the numerator is 2x plus 5, and the derivative in the denominator is 2e to the 2x. Okay, so now I have to stop and think about this limit. What's going on with it? Well, I look at what happens in the numerator as x goes to infinity, and the numerator is going to infinity, and in the denominator it's also going to infinity. So this is still, even after applying L'Hopital's rule, infinity over infinity, but that's okay. L'Hopital's rule can be applied multiple times. Let's see what happens if we do L'Hopital's rule one more time. Well, in the numerator, after I take the derivative, I'd get 2, and then in the denominator I would get 4e to the 2x, and now the numerator is not going to infinity anymore, so we no longer have an indeterminate form, infinity over infinity. The numerator is going to 2, and then the denominator is going to 0, so 2 just goes to 2, but the denominator here, as x goes to infinity, is going to positive infinity, right? So when you take 2 and you divide by a giant positive number, you'd get something close to 0. So the answer here is 0. Okay, let's try another one. In this next example, we have x is going to 0 from the right, and then we have natural log of x in the numerator and cosecant of x in the denominator. So let's think about what's going on here. Now, with the natural log function, I recall that the graph of the natural log function looks like this. So I can see that the numerator, as x approaches 0 from the right, is going to negative infinity. We don't really care about the signs when we're talking about the indeterminate form here. In the numerator, it's, infinite. It's negative infinity, but I don't care about the sign. And let's see what's going on in the denominator there. Now we know that cosecant of x is 1 over sine of x. And so if you start doing cosecant of 0, you're going to get 1 over sine of 0, which is undefined, right? But if it's going to 1 in the numerator and sine of 0 is 0, so 1 over 0 is going to be some kind of infinity, right? In fact, if you're doing 0 from the right, if you think about the sine function, as x approaches 0 from the right, the sine function goes to 0 in the positive fashion. So this is going to positive infinity for the cosecant. So the denominator is going to positive infinity, but again, I don't care whether it's plus or minus infinity. I'm getting infinity over infinity here. And I can't just say infinity over infinity is equal to 1, right? That's not like a real fraction with real numbers. I mean, the answer could be anything. Could be infinity, could be 0, could be 3 with these indeterminate forms like this. In this example, the Hopital's rule applies. We apply L'Hopital's rule here, and the derivative in the numerator is 1 over x, and then the derivative in the denominator, the derivative of cosecant is negative cosecant x, and then cotangent x. At this point, usually after applying the Hopital's rule, you want to think about, can I simplify this expression a bit, make it a little easier? So it is true at this point that it's still of the form infinity over infinity, so I could keep doing the Hopital's rule, but I think it would be ill-advised. I think your derivatives are going to start getting really ugly. So let's see if we can clean this thing up first before we do anything more with the Hopital's rule. I could write this as, just put the 1 over x out front. Now there's the negative, so I'm going to put the negative here out front too. And then 1 over cosecant I can write as sine of x, and 1 over cotangent I can write as tangent. I've still got a problem with the 0 in the denominator here, but I'm seeing something that I remember from earlier times. This is negative sine of x over x. We've seen that limit. We know that one. Times tangent x. And we remember that sine of x over x as x goes to 0. That's our fundamental trigonometric limit, and we know it goes to 1. So that limit exists. We know it. And then tangent of x, That's sine over cosine. So if you would just do direct substitution into tangent, you would get sine of 0 over cosine of 0. So that's 0 divided by 1, which just equals 0. So this goes to 0. So we can evaluate this limit basis of what we know from previous stuff. So we'd get negative 1 times 0, and that just, of course, equals 0. So there's an important lesson to learn here. After applying L'Hopital's rule, see if the expression can be simplified. Because oftentimes, if you start trying to do multiple applications of L'Hopital's rule, it just gets worse and worse. So maybe you can simplify it and you won't need to use L'Hopital's rule additional times. There are some other indeterminate forms that we can apply L'Hopital's rule to, but only after doing some algebraic manipulations first. The first of these types is the 0 times infinity type. Now you might think, well, 0 times anything should be 0, but that's not really true when you're talking about limits. So when we say we have an indeterminate form of type 0 times infinity, what it means is we're taking the limit of the product of two functions, and the first function's going to 0 and the second function's going to infinity. But if the first function's going to 0 more slowly than the second function's going to infinity, then the answer could be infinity. Or it could be that they're kind of the first function's going to 0 at roughly the same rate as the second function's going to infinity, and they're just sort of canceling each other out as you go, and you end up with getting like an answer like 5 or something like that, or pi. You could get basically any kind of answer out of this. But you want to resist the temptation here to think about, just because the limit of one of the terms is equal to 0, it means that the whole limit is 0. It doesn't always work out like that. So the idea on how to solve these is to convert your 0 times infinity indeterminate form to a 0 over 0 or an infinity over infinity, then use L'Hopital's rule. So let's see an example of this. This first example here, we have x is going to 0, and then we're evaluating the function x times natural log of x. Well, you can see that the first factor there, the x term, is going to 0. And then we know that the natural log function, we just did a graph of that a minute ago. As x approaches 0 from the right, the natural log goes to negative infinity. So this is a 0 times infinity type. Again, we don't care about the sign so much. So when we say it's a 0 times infinity type, it could be that the infinity is plus or minus infinity. Okay? So how do we convert this to a 0 over 0 or an infinity over infinity? Well, the trick is to take one of the two factors, put it in the denominator by reciprocating it. So reciprocate one of the factors and stick it in the denominator. And I think you have kind of like two ways you could go about this. One way will work and one way won't. So I could write this as the limit as x goes to 0 of natural log of x over 1 over x. So that's the same thing we started with. I'm not doing a derivative or any kind of L'Hopital's rule at this point. I'm just algebraically manipulating the original expression by taking the factor of x, reciprocating it, and putting the denominator. The other option I could do is to take the original thing and write it as the limit as x goes to 0 from the right of, leave the x in the numerator and then take the 1 over natural log of x and reciprocate it and put it in the denominator. So both of these expressions are the same as the original. Let's look at where we're at now. With the limit on the left that we have here, if you think about x going to 0 from the right, the numerator is going to negative infinity, so we get an infinity going on in the numerator. And as x goes to 0 in the denominator there, the 1 over x, you would get 1 over 0, where the 0 is positive, right? So you would get a positive infinity in the denominator. So this is an infinity over infinity type now. And I can apply L'Hopital's rule, so let's do that. So applying L'Hopital's rule, the derivative in the numerator is 1 over x, and then the derivative in the denominator is negative 1 over x squared. And this is the point, after you apply L'Hopital's rule, you should think, can I algebraically simplify this a bit? And on this one, you sure can. I could rewrite that. When you divide by a fraction, you can reciprocate and multiply by it, right? So this actually reduces to negative x squared over x when you reciprocate the denominator and multiply it times the numerator. And then, of course, that just reduces to the limit as x goes to 0 from the right of negative x. And, of course, that's just 0. So, see, we got the answer of 0 this way. We should look at what's going on the left over there and see if that will work out too. We do have the answer though, so I'm not saying that we need to do the one on the right to get the answer, but we just found out that this limit here equals 0. But let's try this one over here in green. If you look at what's going on with that limit, in the numerator you've got 0, and in the denominator x is going to 0 from the right. That means that fraction in the denominator is going to 1 over negative infinity, which is, if you think about 1 over infinity, that's just 0, right? It's 1 over a large number, it goes to 0. So this is a 0 over 0 indeterminate form. So we could apply Hopital's rule, and when you do so, the derivative in the numerator is just 1. But to take that derivative in the denominator, I'm going to have to use the quotient rule. So it's already kind of feeling kind of yucky, but when you do the quotient rule, you're going to get 0 times natural log of x minus 1 over x divided by natural log of x quantity squared, like that. And then if I algebraically simplify that a bit, it's natural log of x quantity squared. Well, you'll just end up with x times natural log of x quantity squared. So compare that to the limit that you started with at the very beginning in yellow. It's just like actually worse, right? So sometimes when you do the Hopital's rule, you get something that's even worse than what you started with. So I went from x natural log of x to x natural log of x squared. It's still a 0 times infinity, but somehow I just increased the exponent on the natural log of x by doing this process. So, that's sort of a hint that I went the wrong way. So I'm just going to give up on that approach. When you're doing these converting 0 times infinity to a fraction, where you hope to get infinity over infinity or 0 over 0, you've kind of got a 50-50 shot of getting it right. So if you choose one way and it just doesn't seem to be working out, try to convert it the other way. And one thing that you can think about is, of the two factors, the one that is harder to differentiate, that has a yuckier derivative, leave it in the numerator, put the other factor in the denominator reciprocated. Let's apply that rationale to this one. So I've got limit of x squared times sine of 1 over x. When you try to do a direct substitution here, well, you can't really direct substitute, but x is going to infinity, right? So that first factor of x squared is certainly going to infinity. And then what's going on with that sine of 1 over x? Well, the 1 over x itself is going to 0, right? This 1 over x here, that goes to 0 as x goes to infinity. And then sine of 0 is equal to 0, so that whole second factor is going to 0 in the limit. So this is an infinity times 0 indeterminate form. So the trick is to try to convert it to 0 over 0 or infinity over infinity by taking one of the factors and putting it in the denominator reciprocated. The sine of 1 over x is clearly the more complicated factor, right? And when I differentiate it, I would get cosine of 1 over x and then times negative 1 over x squared. So it has a kind of yucky derivative. So I want to leave that in the numerator, because if I put that in the denominator, it's like I would have putting the yucky stuff in the denominator. See, I'd have to reciprocate it and put it in the denominator. Then it'd be really hard to differentiate after I've reciprocated it. So that's the factor I would recommend leaving in the denominator, or leaving in the numerator. So I'm going to take the x squared factor, reciprocate it, and put it in the denominator like this. So leave the sine of 1 over x up there, and then do 1 over x squared in the denominator. So that's the same as the function you started with, just manipulate it a little bit. And now, as x goes to infinity, what's going on is that the numerator is going to 0 and the denominator is going to 0, because 1 over x squared, the denominator of that's going to infinity, so 1 over infinity is like 0. Now I can apply Hopital's rule to it, because it's a 0 over 0 indeterminate form. And I'm going to get the limit as x goes to 0. X goes to infinity. And then the derivative of the numerator is going to be negative 1 over x squared times cosine of 1 over x. And the derivative in the denominator is going to be negative 2 over x cubed. And let's see if we can algebraically simplify this a little bit before thinking about doing Hopital's rule anymore. So if I take that fraction that's in the denominator and then, dividing by a fraction is the same as multiplying by its reciprocal. So if I do that, I would get, the negatives are going to cancel, and I'll get x over 2 times cosine of 1 over x. Okay, so what's going on with this? Is this still an indeterminate form? Well, I can see that first factor, x over 2, if x is going to infinity, that first factor there is going to infinity. Now, how about the second factor? Well, the 1 over x itself is going to 0. So what's cosine of 0? Well, cosine of 0 is equal to 1. So what's going on in this limit is I'm getting the first factor is going to infinity times the second factor is going to 1. So infinity times 1 is just going to be infinity. So this just works out to be infinity because that whole factor there was going to 1. So it's like infinity times 1. You're not literally multiplying infinity times 1, but what we've got going on is that one factor is going to infinity and the other factor is getting close to 1. So if you take gigantic numbers and multiply them times numbers that are close to 1, you're getting gigantic numbers, right? So you get infinity. And this shows us that also when you do L'Hopital's rule and the limit works out to be infinity, that's okay. If you get negative or positive infinity for your limit after you do L'Hopital's rule, that'll be the answer you get. You do have to be careful, though. If you do L'Hopital's rule and then the answer that you get is just does not exist, then you got to just start over. All right, more indeterminate forms. We still have a few more to go. This is kind of a long lesson. The next type that we're going to look at are indeterminate forms of type infinity minus infinity. Now, again, you want to avoid the impulse to go, well, infinity minus infinity must be 0, because when we talk about an indeterminate form of type infinity over minus infinity, we're not talking about, what we're talking about is we have one function that's going to infinity minus another function that's going to infinity. But one of the functions might be going to infinity a lot faster than the other. And so you could get positive infinity or you could get negative infinity, or it could be that they're both going to infinity at roughly the same rate, in which case that difference is going to sort of average out to some number like 3 as you go to, as the limit starts to, as x gets close to whatever value it's approaching. There are a couple of ideas about how to handle these type of things. The first one, and what I feel like is the most common way to do it, is to take the expression and convert it to a single fraction, maybe by getting a common denominator or maybe by doing some sort of multiplying by a conjugate sort of trick. But the idea is that hopefully you convert the resulting limit to one that's of the type 0 over 0 or infinity over infinity, and then maybe you can use L'Hopital's rule. Or you might even be able to just do the limit without using L'Hopital's rule at all. Maybe you can do some algebraic manipulations to simplify it. There's another trick you can do, which I'll show you in a little bit. If x is going to infinity in the example, one thing that you can do is use this kind of interesting fact here, that if you're doing a limit as x is going to infinity, you can convert it to a limit as x is going to 0 on the right. See here, x is going to infinity, but here t is going to 0 on the right. So the trick is you replace x with 1 over t, and then note that as x goes to infinity, 1 over t goes to 0 from the right. This only occasionally works, but I'll give you an example of how you might be able to use it. Let's just do an example here where we do the first strategy of just getting a common denominator and trying to maybe use L'Hopital's rule after getting a common denominator. So in this first example here, x is going to 1 from the right, and then you got 1 over x minus 1 minus 1 over natural log of x. So I'm just going to jump right in by trying to get a common denominator here. So this will be the same as the limit as x goes to... Oh, by the way, before I do that, let me just point out that this is an infinity minus infinity example. As x approaches 1 from the right, this denominator in this first fraction would be going to 0 from the right. So I'm going to put 0 plus to indicate that. So it's like in the whole fraction, then you've got 1 over something that's getting close to 0 positive. So that's an infinity type, and then minus, and then that second fraction, as x approaches 1, natural log of 1 just heads to 0. Natural log of 1 is 0, but if you approach 1 from the right, then it goes to 0 from the right. So again, you're getting minus, and then 1 over something that's getting close to 0 but positive. So that's minus positive infinity. So this is a infinity minus infinity type. You always want to check what type you're dealing with at the beginning before you start jumping and blindly start doing L'Hopital's rule or whatever. Okay. So now that I know it's an infinity minus infinity type, I'm going to try the strategy of getting a common denominator and seeing what happens. So this will be the limit as x goes to 1 from the right. Okay, getting a common denominator, I would write this as natural log of x minus x minus 1, all divided by x minus 1 times natural log of x. And now if we substitute x equals 1 into this expression, let's see what we got going on. In the numerator, you'd get natural log of 1, which is 0. This term here, you're getting 0. And then when you plug 1 into that, you also get 0. So to plug 1 in for x into x minus 1, you get 1 minus 1 is 0. So you can see that you're getting something's going to 0 in the numerator. And in the denominator, this factor here is going to 0. And also natural log of x is going to 0. So the denominator is going to 0 times 0. That's 0. So this is a 0 over 0 indeterminate form. That's the kind that you can apply L'Hopital's rule to. So let's try to do L'Hopital's rule and hope something good happens. So doing L'Hopital's rule, I'd get derivative in the numerator is 1 over x minus 1. And then in the denominator, I would have to do the product rule. So I would get natural log of x plus x minus 1 over x. Now be careful when you're doing L'Hopital's rule that you don't try to do the quotient rule to the whole fraction. L'Hopital's rule says you take the derivative of the numerator and denominator separately. Okay, so now let's assess what we have going on here. It might be that we want to do some algebraic simplification. One thing that you can do when you've got a compound fraction like this is, you can multiply the numerator and the denominator by something to clear fractions. And I can see that if I would multiply the numerator and the denominator by x, which is the same as multiplying by 1, it would clear the fractions. So let me try clearing fractions. So multiply by x in the numerator and you get 1 minus x. And multiply by x in the denominator, you get x natural log of x plus x minus 1. Okay, and then let me think about what's going on here. I can see that it's going to 0 in the numerator. What's it going to in the denominator? Well, it looks like I'm still getting 0 over 0. So this is still 0 over 0. And I don't see any way to algebraically simplify it anymore. So I think I'm going to try to do L'Hopital's rule one more time and hope for something good. So doing L'Hopital's rule, the reason I'm thinking to do L'Hopital's rule one more time is that I can see that the numerator, the derivative is just going to be negative 1. So it's getting simpler. So I do the limit as x goes to 1 from the right. So taking the numerator's derivative, I get negative 1. And in the denominator, I'll have to do the product rule on that x times natural log of x, and I would get natural log of x plus 1 would be that derivative. And then I'm going to get another plus 1 from the derivative of x, and then the minus 1 has a derivative of 0. Ah, this is looking good now. Check it out. If I try to direct substitute 1 in for x into this fraction, I get negative 1 in the numerator, and then I get 0 plus 1 in the denominator. So it looks like my answer is negative 1/2. So you see, infinity minus infinity can work out to be just about anything. And in this case, infinity minus infinity type worked out to be negative 1/2. Okay, let's try another example. So this example, as x goes to infinity, I think you can pretty quickly see that that's an infinity minus infinity that's going on here. Here, unlike the previous example, I can't really just get a common denominator because I'm not even dealing with two fractions here. One thing you can always do with expressions that are a sum or a difference of a term involving a radical is you can multiply by a conjugate. So I think what I'm going to try, it's a little bit of a leap or just a guess, but my instincts tell me that if I took this x minus the square root of x squared minus 3x and I multiply it by x plus the square root of x squared minus 3x over the same thing. So here I'm just multiplying by 1 really. But I know with the radicals that it often helps to multiply by a conjugate if all else fails. And so then if I would multiply this out, then multiplying the terms in the numerator, I would get x squared, and then I'd get minus x squared minus 3x, because when you multiply that radical times itself, the radical goes away. And then in the denominator, you have x plus the square root of x squared minus 3x. And then notice that in the numerator, I just reduce it, the numerator just reduces to 3x, and then we got x plus the square root of x squared minus 3x in the denominator. X is going to infinity. Now, one thing I can see about what's going on here is that this is an infinity over infinity indeterminate form, and I could do L'Hopital's rule, but I think it's going to get yucky because that denominator is going to have a really nasty derivative. So I'm not convinced that this is our best strategy right just yet. I want to try, instead what I'm thinking is, we saw limits like this back when we were in the chapter on limits, when we were doing limits of rational expressions, and we learned that this isn't exactly a rational expression because there's a radical involved, but even when there are radicals involved, we learned that you can do this trick of dividing the top and the bottom by the highest power of x that you see in the denominator. Now in the denominator, you do see an x squared, but it's inside the radical, so that really is kind of acting like just an x. So I think I want to try the trick of just multiplying by 1 over x in the numerator and 1 over x in the denominator. So I'm really just multiplying by 1. So if you do that, you would get limit as x goes to infinity of 3 divided by, when you distribute the 1 over x in the denominator, you'd get 1 plus, and then to multiply that 1 over x times that radical, you need to move the 1 over x inside the radical so that it becomes 1 over x squared inside the radical. So when you pull that 1 over x inside the radical and then distribute it, you get 1 minus 3 over x inside the radical. And now I can look at this resulting expression and go, okay, the only place where I see an x at this point is inside that radical, and you get that 3 over x, and that's going to 0 as x goes to infinity. So at this point I can see, I can just evaluate this limit and get 3 over 1 plus 1, because that 3 over x goes to 0, so you're left with the square root of 1 there. So this comes out to 3/2 actually. Just notice here that I never used Hopital's rule. Now, there was a point where I could have used it at this point here, circled in green, but I chose to go a different route at that point. And the reason I chose to go a different route was because I already tried to do this problem, and I tried to do Hopital's rule, and it didn't work. So I was saving you the trouble of seeing all the mess. However, you can do this problem with Hopital's rule. Let me show you how you can. So the way you can do this with Hopital's rule is to take advantage of this fact that I told you a minute ago, is you convert the limit as x goes to infinity to the limit as t goes to 0 on the right, where you substitute 1 over t in place of x. So if you do that trick here, this would become the limit as t goes to 0 on the right, and you just go through the original limit, and everywhere you see an x, put 1 over t. So this would become 1 over t minus the square root of 1 over t squared minus 3 over t. Now at this point, it's still pretty yucky. It's still of the type infinity minus infinity, and it's not clear how I can use Hopital's rule at this point. But let me do a little algebraic simplification first. So I'm going to leave that 1 over t alone, but inside that radical I'm going to get a common denominator so that it looks like it'll be 1 minus 3t over t squared, like that. And then, when you take the square root of a fraction, you can take the square root of the numerator and denominator separately. And when I take the square root of t squared, I'm going to get t, because t is positive. I don't have to have an absolute value. So this will be limit as t goes to 0 on the right of 1 over t minus the square root of 1 minus 3t over just t. Now I can put that into one fraction. It'll be 1 minus the square root of 1 minus 3t all over t. And when I look at what I've got here, notice that when you substitute t equals 0 in, you get 1 minus 1 in the numerator, so it's 0 in the numerator and it's 0 in the denominator. So now it's a 0 over 0 indeterminate form. So I can apply Hopital's rule, and the derivative in the numerator will become 1 minus, you'll get negative 3 over 2 square root of 1 minus 3t after you use the chain rule on that. Then you just have 1 in the denominator there, right? So now think about what happens when you plug in t equals 0. It's no longer an indeterminate form, and you don't run into any infinities either. Only thing that's going on here is that this term right here, the 3t, goes to 0, and so you're left with 1 minus negative 3 over 2 times the square root of 1. Oh, I'm sorry. When I took the derivative previously, I should have got 0 right there. The derivative of 1 is 0. So even so, you get negative 3 over 2 square root of 1. Well, it's negative, and then there's a negative 3 at the top too, so it's a double negative. So you just end up getting 3/2, which I believe is the answer that we got when we did it the other way. Let me double check that. Yeah, we got 3/2. So I feel good about the answer, getting it 2 different ways. So in this example, we did use Hopital, and maybe the algebra was a little less complicated doing it this way, but it involved doing this trick in green here where we convert the limit involving x goes to infinity to a limit as t goes to 0 on the right. So I think this is a trick that you won't use that often, but it's nice when it does work. Okay, so there you go, there's that. Okay, so now we've got a few more indeterminate forms to look at. They're so-called these are all exponential forms, and you got these three different types: 1 to the infinity, 0 to the 0, and infinity to the 0. Again, we're not literally talking about just taking 1 and raising it to the infinity. What's going on is we're going to have a function, like what we're really looking at are limits like that look like this down here in yellow. There's a function in the base, and then there's a function in the exponent. And for the 1 to the infinity type, it just means that when you take the limit of the f of x, it's going to 1, but then the g of x and the exponent's going to infinity. So it's a little bit of a race. The base going to 1 is wanting to make it just come out to 1, right? But the exponent going to infinity is wanting to make it grow large, or possibly small, depending on whether the number's less than 1 or bigger than 1. So there's a little bit of a tug of war going on between the base f of x and the exponent g of x. Same thing when you do 0 to the 0. You might be thinking, well, anything to the 0 is 1, but the base being 0 makes it want to be 0. So there's a little tug of war going on there between the exponent and the base. And similarly, infinity to the 0, you want to go, well, if I raise it to the 0, I should get 1. But the base is going to infinity. So you're taking something that's getting really big, and then you're raising it to a power that's getting small. Which one's going to win, the base or the exponent? The way that we do these, though, is we use a conversion. So when we're doing the limit as x goes to a of f of x to the g of x, we convert it to an exponential with base e like this. So we go, this is the same as the limit as x goes to a of e raised to the natural log of that stuff, f of x to the g of x. And we know that there's a property of natural logs that says that when you do natural log of something that has an exponent, you can bring the exponent down in front of the logarithm. And so you can actually write this as e to the limit as x goes to a, and the limit you're going to be taking there is g of x times natural log of f of x. So the idea is, if we can evaluate this limit in blue, then your answer to the original question will be e to whatever that limit is that you evaluate in blue up there. So let's see if we can do this for a few examples. So here's an example, sine of x to the x. So what kind of indeterminate form are we dealing with here? Well, as x goes to 0, the base is going to 0. And then also the exponent's going to 0. So this is a 0 to the 0 indeterminate form. And that's one of the three that's covered by this strategy. If you got an exponential and it doesn't work out to be one of these three forms, it's not indeterminate. You can get an answer. Like if you see something like infinity to the infinity, that's infinity. That's not indeterminate. Or if you see something like 0 to the 1, that's not indeterminate. That's 0. Or if you see something like 1 to the 0, that's not indeterminate. That's 1. So things like that. But anyway, this one is 0 to the 0, which is one of our indeterminate forms. So what we're going to do is do exactly what I showed you above. Is we're going to convert this to the limit as x goes to 0 on the right of e to the x natural log of sine of x. I went ahead and pulled the exponent down after I took the logarithm of it in the exponent. And then what you can do is pull the limit up into the exponential, because the exponential is a continuous function, so it allows you to do that. So at this point, really the limit that we need to work out is this limit up here. So at this point, it's kind of nice to just go ahead and separately work out that limit. So what is the limit as x goes to 0 on the right of x times natural log of sine of x? Well, think about when you plug in 0 here. When you plug in 0, that first factor of x is 0, and then you'll have natural log of sine of 0. Sine of 0 is 0, and the natural log of 0, well, is undefined, but we're talking about what happens as x approaches 0. So the sine of x here is going to 0 from the right, and then natural log as its input approaches 0 from the right goes to negative infinity. So this whole factor here is going to negative infinity. So this is a 0 times infinity indeterminate form. And we have a strategy for dealing with those. The strategy was to take the simpler factor, reciprocate it, and put it in the denominator, and then use the Hopital's rule. So that's what we're going to do here. So we're going to get limit as x goes to 0 on the right, and we got natural log of sine of x we're going to leave in the numerator, and then we'll have 1 over x in the denominator. And so now we will do the Hopital's rule, because this is an infinity over infinity form. So using the Hopital's rule, the derivative in the numerator works out to be, we do 1 over sine of x times the derivative of sine of x, which is cosine of x. And then in the denominator, you get negative 1 over x squared. Let's try to clean this up a little bit before we proceed any further. So this is limit as x goes to 0 on the right of, looks like we could write it as negative x squared times 1 over sine of x times cosine of x. The thing that strikes me on this one is that I could write it as limit as x goes to 0 on the right of negative x times x over sine of x. I like x over sine of x because I know the fundamental trigonometric limit times cosine of x. So I can look at what all these factors are doing here. X is going to 0, so that factor of negative x is going to 0. X over sine of x, that's the reciprocal of the fundamental trigonometric limit, but we know that that goes to 1. And then cosine of x, well, cosine of 0 is equal to 1, so this factor goes to 1. So the grand total here is 0 times 1, and you get 0. But that was the limit of the exponent up here. So my final answer is going to be e to the 0, which is equal to 1. So in this case, 0 to the 0 came out to 1. Let's do another example of this sort of thing. I think you need to see it a couple times at least. So let's evaluate what kind of indeterminate form are we talking about here. Well, as x goes to infinity, in this example, the 1 over x here is going to 0. So the base of this thing is 1 plus 0, so it's 1 in the base, and then the exponent's going to infinity. So this is a 1 to the infinity indeterminate type. And that's one of the 3 indeterminate types we mentioned at the top that our trick is going to apply to. So let's try our trick. So this is equal to e to the limit as x goes to the infinity of whatever the exponent was times natural log of whatever the base was. So like this. And now this limit, we're going to evaluate it separately. So the limit as x goes to infinity of x natural log of 1 plus 1 over x. What's going on with this? Well, as x goes to infinity, the x factor there is going to infinity, and then natural log of 1 plus 1 over x. What's inside the natural log is going to 1, and the natural log of 1 is 0, so this is infinity times 0. So our trick for dealing with those is to take the simpler factor, reciprocate it, and put it in the denominator. So this will be the limit as x goes to infinity of natural log of 1 plus 1 over x divided by 1 over x. And at this point, we've got ourselves a 0 over 0, put it down here, 0 over 0 indeterminate form. And so then we're going to use the Hopital, and we'll have limit as x goes to infinity. The derivative of the numerator, we could have saved ourselves some trouble, I guess, maybe by using properties of logarithms and getting a common denominator, but I'll just go ahead and go with it like this. So derivative of natural log of 1 plus 1 over x, you're going to have 1 over 1 plus 1 over x times the derivative of the inside, which is negative 1 over x squared, and then the derivative of the denominator is negative 1 over x squared. And I see that those factors cancel there and there. And now if I let x go to infinity, in what remains, all that's going on is that 1 over x is going to go to 0. And what are you left with? Looks like to me, the only thing that's left is just the constant 1. But that's not our final answer. That was just the limit of the exponent. So this was the limit that we worked out up here. So our final answer is e to the 1, or just e. Isn't that interesting? That limit involving doesn't look like it has anything to do with e, actually works out to e. In fact, this is one way that you can define what e is. You can define e to be that limit. Or you can do the trick where you say, the trick that we did in a previous problem where if x is going to infinity, you can replace that with t is going to 0 on the right, and then it would become 1 plus t to the 1 over t. This is one way that e is often defined too. So anyway, there you go. One last thing to mention here is that, you know, when we look at these limits of f of x over g of x, it kind of gives us a way to compare how fast these functions grow as x goes to infinity. You can imagine that as we let x go to infinity, maybe both of those functions, f and g, they're both going to infinity, but we want to know, you know, which one's going to infinity faster. In other words, which of these functions grows faster? Well, if you think about it, if you take that limit in yellow there and it comes out to 0, that means that the denominator was getting big compared to the numerator. And so that means that the denominator was the faster growing function. And then we actually have a little notation for that to indicate one function's growing faster than another. This notation here. So that notation looks like two less thans next to each other, indicates that the function f of x grows more slowly than g of x as x goes to infinity. And likewise, if you take that limit in yellow there, maybe you use Hopital's rule or whatever, but let's say that the answer comes out to infinity. Well, that means that in that fraction, the numerator was getting bigger than the denominator. So in that case, we would say that the numerator f of x grew faster than the denominator g of x. It can also happen, and we saw examples like this, that maybe the numerator and the denominator are both going to infinity, but after you do L'Hopital's rule, you find that that limit in yellow at the top works out to be like 5 or something like that. Well, if that happens, then it means that those two functions are kind of going to infinity at the same rate in such a way that neither one really wins the race, right? The numerator didn't force it to go to infinity, or the denominator didn't force it to go to 0. So if it comes out to some number like 5 that's bigger than 0 but less than infinity, then we use this. We say that f and g grow at comparable rates. So let's apply this to compare the functions. I want to compare square root of x and natural log of x. As x goes to infinity, we know both of those functions go to infinity. And I could go look at a graph of these two functions, and when you look at the graphs of these functions, they don't look totally dissimilar. So if you go to Desmos and you graph square root of x and natural log of x, the one in red is the square root of x. It looks like it grows a little slower than the natural log, but man, I don't know. It's hard to tell. Maybe as x goes to infinity and you look at the ratio of those two functions, maybe it'll come out to like 10 or something. I don't know. So let's just see. Let's compare. I want to compare their growth rates. So let's look at the limit as x goes to infinity. I'll put natural log of x in the numerator and square root of x in the denominator. And we see that this is an infinity over infinity indeterminate form, so we can use L'Hopital's rule to evaluate the limit. And the derivative in the numerator is 1 over x, and the derivative in the denominator is 1 over 2 square root of x. So this will, when I simplify it, its limit as x goes to 0 of 2 square root of x over x, which actually you can simplify because it's x to the 1/2 in the numerator. So you could write this as limit as x goes to infinity of 2 over the square root of x, and that clearly goes to 0. So what does that tell us about the growth rates? It tells me that if you look at the limit of the original limit, natural log of x over natural log of x over square root of x, and you get 0, that means that the denominator was the faster growing thing. So the denominator won the race. So then I would say this is telling me that the square root of the natural log of x grows slower than the square root of x. In other words, the square root of x grows faster than natural log of x. So we'd use that notation down there at the bottom. So even though their graphs look like their rates might be comparable, they're not. Square root of x really goes to infinity a lot faster than does natural log of x. And here's a little summary if you would compare lots of different types of functions. So at the lower end of the scale here, you have a natural log function raised to any positive power. So like that could be natural log of x to the 1/1,000,000th power. It doesn't really matter how big that exponent is. That will grow slower than any power of x. So x to the p, where p is a positive power. Natural log of x, it doesn't matter. It's amazing. So natural log of x, if you raise that to the 1,000,000th power, it'll grow slower than x raised to the 1/2 power. And then x to the p in turn grows slower than x to the p when you multiply it times one of those, like a natural log to the q. And then that product in turn grows slower than if you just did x to the p plus q. And so then x to the p plus q, that's just some power of x. No matter how big that power is on x, it'll always grow slower than an exponential function where the base is greater than 1. So like x to the 1/1,000,000th power will grow slower than 2 to the x, or even 1.01 to the x. And then all of these grow slower than x to the x. So it kind of gives you, it's nice to know, like kind of have a sense of how functions compare. These are all pretty common types of functions. So in the first example here, how does the growth of natural log to the 100th how does the growth of that compare to the 7th root of x? Well, according to the thing in yellow there, natural log of x to the 100th, that's like q, and then you compare that to 7th root of x, that's x to the 1/7. So that 1/7 is like the p. Like this theorem says that it doesn't matter what p and q are, p could be small, q could be big. It's still the case that natural log to that big power still grows slower than x to that small power. So this is how they compare here. Or in words, i.e. 7th root of x grows faster than natural log of x all to the 100th power. And then how does the growth of the exponential function 1.01 to the x compare to x to the 100th as x goes to infinity? Well, x to the 100th, that is a polynomial sorted term. So that would be like your x to the p up there. So what we're doing is we're comparing x to the p here with something of this form, b to the x. And so we know the b to the x grows faster. It doesn't matter that the base was just a little bit bigger than 1. Eventually, the exponential wins the race. So that's your comparison there. Okay, I think I'll stop there. I would tell you that I'll talk to you again soon, but only if you end up taking Calculus 2 with me. And I'm not teaching Calculus 2 anytime soon, so I guess this is our last video together. So I'll just bid you adieu and hope that you continue your studies in calculus with a good foundation from here. Bye-bye.